Hello, you're welcome back. Okay, so now we continue from where we stop. Okay, so here we're looking at vibration in a column, all right? Okay, so we already know that sound is being produced whenever materials are being set into vibration, particles are being set into vibration. Okay, now that sound that is produced can be a noise because it's not coordinated, and it can be a music because it's coordinated. So basically, we know that when air is set into vibration, then definitely sound is also produced, and and that is how most wind instrument is being constructed. For example, trumpet, people blow air into trumpet and they produce musical tone, right? And that's what we're going to be looking at. Okay, so in this video, we'll look at reflection because anytime air is being set into vibration in a pipe, there's bound to be a reflection will occur. And that reflection, okay, will actually create different musical tone, and we're going to look at all these musical tone and their frequencies. Okay, so we are looking at basically two types of pipe. Okay, one type of pipe is a closed pipe. That's a pipe that's that's closed at one end. Of course, the air is being blown at the open end of the pipe, right? The other end is closed. Now once that happens, as you can see, I have, you see me atomizing node and antinode of the wave that is being generated. Okay, of course the air inside the pipe will be set into vibration, and the wave that is generated by the air inside the pipe, please pardon me, the wave that is being generated, as you can see, this is the wave. This all what I'm showing here is vibration of the air. Okay, just like what happened in hurricane. All right, just so that simply means that the air will be set into vibration to generate a wave, and that type of wave, remember, for sound is basically longitudinal wave. But in this case, it's not just longitudinal wave, it's a longitudinal stationary wave. Why? Because it has a node. Okay, it has a point where it is being reflected. So for a closed pipe will generate, okay, the sound, the air inside the pipe will generate, okay, a wave, a stationary wave for that matter, and the close end of that pipe is where we get our node. Remember, our node is always the fixed point, that point where the two wave, okay, actually reflect. So for a closed pipe, the close end will always be the node of the wave, while the open end, okay, will always be the antinode. Please take note of that. The close end will actually be the node of the stationary wave, while the open end is the antinode. But for an open pipe, all right, as you can see in this diagram, an open pipe, okay, has its both end opened, and of course, if the both end is open, remember, once the air in this pipe is being set into vibration, the open end of both sides will always be antinode. Okay, so the question, where do we have our node? Our node now becomes, will be seen at the midpoint of the pipe. All right, so now, having introduced this, so we're going to start with the frequencies that is produced whenever a column is being set into vibration in a pipe, and we're going to start with that of the closed pipe before we look at the open pipe. So remember, the whole idea of actually setting the air into vibration is to produce musical tone, and that musical tone will always have a frequency, right? So we're going to look at the very first frequency that is produced in a closed pipe. Now, how do we get to know the very first frequency that is produced in a closed pipe? Okay, is actually produced, and of course, don't forget that we need to actually measure the length of the pipe of the air column. Okay, the length of the pipe is equivalent to the length of the air column that's set into vibration. Okay, so now the very first frequency in a closed pipe will be generated, okay, um at the point where we already know that the open end is the antinode and the closed end is the node, right? And we know that the distance, the length of the pipe, okay, is actually antinode. Is always, remember, the open end is antinode and the closed end is the node. And we know already that the distance between the node and antinode, we talked about that, is always quarter wavelength. Hope you can still remember when we did stationary wave, okay? When we did stationary wave. So we should know at this point, okay? This is the antinode. And this is the node. So the distance between the antinode, consecutive antinode and node is always water wavelengths. Okay, don't forget that. So if that being the case, that means the entire length of the air column will generate a quarter wavelength. So that means from here now I can cross multiply. So invariably now the wavelength is going to be equal to 4 times the length of the air column 4L. So now let's now go to what we want to do with this. Don't forget our velocity of every wave is given as lambda f. My whole interest is to get the very first frequency, which of course is v all over lambda. Okay, the v is the velocity of sound in air, which all right is constant, and the lambda here is 4L. So the very first frequency that is produced, okay, by a closed pipe or by any pipe at all is what we call the fundamental frequency. So this frequency now is the very first frequency, okay? So that means the very first tone that you will hear whenever someone actually blow into a pipe to produce music, the very first note is called the fundamental frequency. So for a closed pipe, all right, the fundamental frequency F0 is given by the formula V all over 4L. So invariably now, if I should have a closed pipe of length 20 cm, then I'm being asked to find the very first frequency you get out of this closed pipe. Simple. All I just need to do is just to evaluate V all over 4L. Velocity of sound in air is, okay, approximately 340 meters per second or 320 approximation, right? Then 4 times the length of the air column, 20 cm, convert it to meter. That should give me 0.2 meter. So just evaluate that. Now the question is, after the very first note, okay, don't you have other notes? Don't you have other frequencies apart from the very first? Yes, we have others, right? We have other frequencies, and that's what I'm going to be looking at. And what are the other frequencies called? Other frequencies are called overtone or harmonics. So remember the overtone I told you of, okay? All right, so other frequencies are called overtone or harmonics. Now, don't forget, for a closed pipe, the fundamental frequency is equal to V all over 4L. I would have loved to generate a formula for the overtones, but I will not have to stress that, okay? Go through that stress. I'll just give you how it is being generated. After the fundamental, this is the fundamental quite well. Let me take it away from here. Okay, what we have is the fundamental. So now the overtones are the multiples for a closed pipe. For a closed pipe, the overtone are always odd multiples of the fundamental frequencies. All right, so which simply means that the very first overtone, okay, or first harmonics is going to be the very first odd multiple. What's the odd multiple apart from 1? Okay, multiple odd numbers are goes 1, 3, 5. Okay, so that means first harmonics is gonna be the first odd multiples of f0, that is 3 times f0. Okay, so which can be 3v all over 4l. Simple. Just remember that the harmonics of a closed pipe are odd multiples of the fundamental frequency. So that means the second harmonics now, okay, with respect to the fundamental frequency, will now be the next odd multiple. The next odd multiple is 5. So on and so forth. So that's gonna be 5 times v all over 4l. So with what we have previously now, okay, or better still, a situation where I have calculated fundamental frequency to be, let's say 340, okay, like what we did previously, all over 4 times 0.2. Let me do this to the end. Okay, so it's going to be 340 divided by 0.8. Okay, so let's let me not stress myself. Let me get a calculator. So I have 340 divided by 0.8. So okay, so let's say that pipe, okay, that closed pipe, all right, after calculating the fundamental frequency, gave me 425 Hz. This is just the very first step. Okay, with this fundamental frequency, the question is, how can I get the overtones? For example, let's say, okay, we are being asked to find the second overtone. Okay, so the second overtone, simple, is going to be equal to 5 times that fundamental frequency, and I've already calculated the fundamental frequency, so that's going to be 5 times 4, please pardon me, 5 times 4 to 5. Let's do that. 5 times 4 to 5. So okay, invariably now we're having 2125. Okay, 2125 Hertz. 2125 Hertz. Okay, so you can still go on. If you can still go on to go get the third overtone. Once you know the odd numbers and you know your fundamental frequency, then you can get any overtone or harmonics. The third will be 7. So always remember that it's gonna be 7 times 4 to 5. Okay, I will actually leave that for now. If there's any need for us to return back to the closed pipe to prove more formula, we'll come back. But let's look at the open pipe. Okay. Now the question is, for an open pipe, how many wavelength do I have? Remember, for an open pipe, okay, I have 2 antinodes. I've already shown you that. I have 2 antinodes. Okay, I have 2 antinodes. So that means the open end, there's an antinode here. At this open end, there's another antinode here. At the other open end, then in between there's a node. So let's look at the distance. So the entire distance of the air column. So the entire distance of the air column, you know how it is now. I mean, from one antinode to a node that is quarter wavelength. The same thing happens from this point to this point. Okay, so another quarter wavelength. So that means the entire length now will now be 2 quarter wavelengths, lambda all over 4 plus another lambda all over 4. And that should give us a lambda all over 2. Okay, if I'm not mistaken. Yeah, I'm not. Okay, so from here now, I can simply get my wavelengths, okay, because I need it. If I cross multiply, don't forget, I'm going to have two times the length, okay? So the wavelength is 2 times the length of the air column. Okay, having done that now, so the velocity of an open pipe, or the frequency, the very first frequency known as the fundamental frequency. Fundamental frequency. Okay, which of course is we use F0 to represent of an open pipe is giving us the velocity V, of course all of that the wavelength, okay? That's V all over the wavelength is 2L. The wavelength is 2L, okay? So please take note of that. Now the question is, okay, this is my fundamental frequency, which is just easy, okay, by the formula I have actually generated there. But then, how about the overtone, all right, or harmonics? Overtone or harmonics. Okay, so now, in the case of an open pipe, the overtones are related to the fundamental frequency by integers, okay? Integers, can call it integral, can I call it integral? Now, integer multiple, right? So what simply means that it's not all numbers, it's not even the all integers apart from 1, because F0 is just is the first, right? So this the very first overtone is going to be equal to 2 F0. Second overtone, so all, so I'm not skipping any number, all are possible, so the second will now be 3 F0. Third, it goes on and on and on, 4 F0, 5 F0, 6 F0, so that's how it actually continues. I hope that is well understood. Okay, so invariably now let's say this pipe here with a length of 10 cm, okay, produce a tone in air whose velocity is let's say 320 meter per second. Okay, and you're being asked to find the, let's say, the third overtone. All right, third overtone. First of all, I have to get the fundamental frequency. So the fundamental frequency of such is going to be equal to V all over 2R. So it's going to be V, which of course is 320. Okay, so I use what I've been given as the velocity of the velocity of sounding air, right? 320. Then divided by 2 times the length of the air column, that's 10 cm. If I convert to meter, okay, 10 divided by, that's 100, right? 0.1. All right. So that's going to be 320 divided by 0.2. All right, okay, so now 320 divided by 0.2 divided by 0.2. 1600. So in this case, I'll have the fundamental frequency to be 1600 hertz. Okay, so what am I even looking for? Okay, let's say fourth overtone, right? Remember, first is second. That means the fourth will be 5. Okay, first is second, the fourth will be 5. If I go first is second, the second is first overtone is 2 FO, second is 3 FO, third is 4 FO, then fourth is 5 FO. All right, so five F0. Okay, 5 times whatever I had 1600. Okay, so we can still come back to this, but then let's proceed. Now I'm done with vibration and of course the production of musical tone in air column. All right, but let's look at how it works in a string. Vibration. Okay, in stretch string. Of course, you know very well that stretch string can be set into vibration to produce a tone, as in what we have in musical guitar or piano. Those are string instruments. Okay, now before I actually look at the basically, okay, here the fundamental frequency. Okay, this whenever string is being set into vibration, there's still going to be a fundamental frequency and there's just going to be overtone. Okay, but one thing, I don't have to go through the proving of any formula. The fundamental frequency, the formula for the fundamental frequency of data of a stretch string, is the same as that of an open pipe. They have the same overtone, so the fundamental frequency still remains V all over 2L, and the overtone, okay, still remain all integer multiples. So everything that we did previously is applicable to this, but I am not gonna okay, put my attention on the formula for the fundamental frequency. I'm gonna look at the relationship between the frequency of a string that is set into vibration, okay, with the tension of that string, because anytime a string is being stretched, there's a tension. All right, and of course that string will also have length, because we value the frequency of a stretched string by varying the length. People that play guitar, all right, once they are playing guitar, they'll be touching the fret of their guitar at different position, different lengths. So telling you that different length where you touch the string, okay, you are varying the length, and of course you are varying the frequency. So the frequency, okay, of a stretch string is actually given by the formula 1 all over 2L, then the square root of T all over M. From this formula now, we can actually conclude that, okay, the frequency of a string that is stretched is inversely proportional to the length from this formula. So that means if I want more frequency, I'll reduce the length. And that is what happens whenever people playing instrument play octave. They will come close to the they come very close to the base of the guitar. They come very close to the base of the guitar, just to reduce the length for a high frequency. Okay, All right, so please take note of that. And of course, here too, we can also conclude that the frequency of a stretch string is directly proportional to the square root of the tension. The more the tension of the string, that means the more that string is being stretched, okay, to give it more tension, because by the time the string is, you stretch a string much, all right, it will have much tension, and that will also increase the frequency. But the frequency is inversely proportional to the mass of the string, to the square root of the mass of the string. That means tiny strings, okay, with a small mass have higher frequency, while large strings, okay, with a large string with of course large mass, okay, have a lower frequency. That is why when you go to difference between bass guitar, if you see people that play bass guitar and people that play lead guitar, that's they are all guitar with strings, okay, and people pluck the strings to generate musical tone. But the difference is that for a lead guitar the strings are very tiny, so to give you that tiny frequency, okay, that tiny pitch. But a bass guitar have a very large or string with a large mass, okay, that reduces its frequency, and that is why you have that bass sound from a bass guitar. Okay, so I hope that is well understood. So this is just to illustrate the relationship between tension, mass, and length as it affects the frequency of a stretch string. Okay, so we are actually coming to the end of this. So invariably now let's look at a musical instrument. So we can conclude by looking at different musical instruments. All right, so musical instruments are being classified as follows. Okay, we've talked about the wind instrument, right? Wind instrument. Number two, I just talked about the string instrument. Then the other one is what is called the percussion. Percussion. All right. Of course, wind instrument is the tone is being generated by the vibration of a column, and we have an example. E.g., we have flute, or have trumpet. All right, saxophone, EDC, recorder, string. We have guitar, violin, piano. The piano I'm talking about is actually the olden type of piano, not the electric piano, okay, that we have that generate electric signal. Then percussions include all types of drums. Okay, basically, so the only thing, if there's any other information, by the time we start solving examination question, okay, I will introduce other information. But take note of this basic term concept and the formula I've given you in this tutorial. All right, see you in the next tutorial. Thank you.